This is the 10th video in our series on topology, and today we're going to talk about the quotient topology. And the general idea of the quotient topology is you take a topological space and then you want to either glue or shrink certain regions of that topological space, well, to create a new topological space in order to really study different shapes, if you will. But that's not a very careful way of writing it down, so we will build up a careful way of writing it down. But before we do that, I'd like to look at some intuition building examples. So let's say we start with the closed interval from 0 to 1 and we glue the two endpoints. So we glue 0 with 1. So that pretty clearly creates a circle. It's like we're tying a piece of string to, well, one end of it to another end of it, if you will. And then I'd like to also notice that the following set right here from, well, let's say that's a 3/4 or something, it doesn't really matter where it is, up to 1, including 1, is open in the subspace topology over here in 0, 1. And then, well, where does that get mapped to over here? Well, so that gets over here mapped to this thing right here, which is not open. And then that actually means that our maybe map that does this gluing is not an open map, because observe that it takes an open set over here in the subspace topology. Observe that this is not open in the real numbers with the Euclidean topology, but it is open in the subspace topology. Whereas that thing over there is not open in, well, maybe we would think of that as the subspace topology inside of R2, if you will. But observe that if we go over here and add another part to this open set, which maybe goes from 1/4 down to 0, notice that's the union of two open sets, which is open in the subspace topology. And now we have an open set over here. It's like this kind of interval on the circle, if you will. And now, if we start with an open set that maps to an open set, that's called a saturated set. And that's really the type of open set that's going to be most important to our study in this quotient topology world. Okay, so let's look at another example. And this example is built out of the square 0, 1 cross 0, 1, so the unit square. And we're going to do like two little examples of this all at once. So let's say we glue the top and bottom edge, but we keep the orientation of each edge the same. So that means we're gluing this point 0, 1 to this point 0, 0. We'll be gluing this point right here to this point right here, this point right here to this point right here, and then these endpoints 1, 1 to 1, 0. So put all together, that means that we're gluing the point x0 to the point x1. Well, I think that pretty clearly makes a cylinder. And we could show this maybe orientation preserving gluing by putting two arrows right here, just to say that we're gluing it in that direction, if you will. And I should say that that's like a standard way of writing that. And now, well, let's observe that we could play the same game in this setup as we did in this setup with open sets. So notice that this thing right here, assuming it's got a dotted boundary, is open in the subspace topology. But it's not going to be open when we send it over there under this, well, what will eventually be a quotient map. Let's say the seam is on the front side, and let's say the seam is right there. Then this open set right here would map to a not open set. Maybe it would be something like this. It would include that line right there, making a not open set. But if we were to add to this some sort of copy down here that has the same boundary, if you will, then we would produce an open set over here. And so again, the first example, before I amended the drawing, is an example of a not saturated open set. But the second example is a type of open set which we call a saturated open set. Okay, so now, well, what if we do the same kind of thing with the unit square, but we glue it in opposite directions? So maybe the orientation of the lower edge is opposite the orientation of the higher edge. And so we could notate that by putting a reverse arrow. That means that 0, 0 will be glued to 1, 0. 1, 0, or sorry, 1, 1. 1, 0 will be glued to 0, 1, and then maybe this point right here to this point right here, and so on and so forth. So in other words, we're gluing it with a twist. You can think about pulling this out of the plane, maybe stretching it this way, performing a twist, and then gluing it back together. Well, in that case, you get something called a Mobius strip. So there's my attempt at a picture. You could maybe Google a Mobius strip to get a better picture if you want. And maybe the gluing procedure could be defined by x0 is glued to 1 minus x1. Okay, let's look at a couple of more intuition building examples before we jump into the careful way of looking at this stuff. Okay, so here are two more examples. So the first one is going to start with the unit square, but now we're going to, keeping the same orientation, glue the bottom edge to the top edge and the left edge to the right edge. Now, the first gluing will create a cylinder, and then the second gluing will be to fuse the two ends of that cylinder, but notice that that's going to make a donut shape, or in other words, a torus. And if we want to follow where these edges go, so let's say this green thing is glued to this green thing. Well, let's see, that's going to give us a circle over here. Now, where that circle is kind of depends on the exact gluing location. And then this peach-colored thing, well, that's going to give us a circle around this end. And, well, actually, those could be switched. It depends on maybe the order of operations of the gluing, but in this case, it doesn't really matter which one is done first or second. We get the same picture. The only difference would be what colors we get over there for our circles. Okay, so now let's look at another example, and that would be this closed disk, or the closed ball of radius 1. So that's going to be everything in R2, xy, where x squared plus y squared is less than or equal to 1. And now what we want to do is take the entire boundary and glue it to a point. And so this isn't the same thing as we did in the previous ones where we just glued things together. Here we're like collapsing the entire boundary to a single point. And so that would be like this shrinking. But observe that if we take this entire boundary and identify it with a single point, that's going to give us a sphere. You can think about wrapping all of this up into a sphere. And then, well, we could just take that point to be the northern pole of the resulting sphere. Okay, so now that we've looked at some intuition building examples, let's see how we can do this carefully. All right, so here's our first definition. So let's say we've got two topological spaces x and y, and then we've got a surjective function p from x to y. Then we say that this function is a quotient map if it satisfies the following condition. So v and y is open if and only if the pre-image of v in x is open. So let's observe that the forward direction here is a condition on p being continuous. And you might think that the reverse direction is a condition on p being an open map, or p inverse as a function being continuous. But let's observe that p inverse may not exist because this is just a surjection. That means it may not be a bijection. So the fact that this looks like a definition of a homeomorphism from what we saw previously, but just without the bijective part, that's kind of important here. Okay, so now let's look at a first example. So let's take x to be this union of the intervals 0, 1 with 2, 3. Those are both closed, and we're putting the subspace topology on that. And then y is the interval 0 to 2. And then our function does the following. So p of x is just x if x is between 0 and 1, and it's x minus 1 if x is between 2 and 3. So that tells us how p acts on these two disconnected parts of our domain. And so let's observe that this simply glues these two endpoints together. We can actually, maybe with colors, describe where points go. So notice everything between 0 and 1 will be mapped to everything between 0 and 1. I think that's pretty clear just because it's the identity map there. And then the number 2 will get mapped to the number 1. And so that's our single point of this thing being not 1 to 1. And then everything between 2 and 3, notice it gets decreased by 1, so it's going to get mapped here. So seeing it like that, I think it's pretty clear that we have this gluing thing happening. The points 1 and 2 are glued together. Okay, now how could we, maybe if we wanted to, carefully check that this is a continuous function or that it satisfies this rule over here? Well, I think maybe the best way to do it would be to look at, instead of pre-images of arbitrary sets, we could look at pre-images of, let's see, basis subsets, or yeah, elements of the basis of the topology. So let's just sketch some of the things. So the basis for the subspace topology on Y. So we looked at this before, but they are sets of the form, let's see, 0B, including 0 but not B, where B goes between 0 and 2. So that would be one flavor of open set. Or we could have A to 2, including 2 but not A. And here A could go from 0 to 2. Or we could have just the open interval A, B. So let's see, that's going to be A less than B, all between 0 and 2, not including either one. And then, well, notice that the pre-image is going to depend on the size of these things right here. So let's, for instance, look at the pre-image of the interval 0 to B, including 0 but not B. So I'll sketch some examples of that over here. Maybe I'll put it below. So that would be something like that. So that would be an open set over here. Notice that since it stops before 1, something particular is going to happen when we take its pre-image. Or we could have one that goes up to between 1 and 2, and then something particular there is going to happen to its pre-image. So maybe, let's see, if we've got something like this, then the pre-image is going to be 0b if b is less than 1. So I think that's pretty clear, actually less than or equal to 1. And then it's going to be 0, 1 union, and then 2 to b plus 1 if b is bigger than 1. Again, I think that's also pretty clear. So if we wanted to, for instance, go over here and look at the open set in the subspace topology that goes from 0 to maybe 3/2, observe that the pre-image of that will go from 0 to 1. And then our next bit over here would start at 2, including 2, and then it would go up to, well, let's say 5/2, not including 5/2. So there's the pre-image of that magenta set over there. Okay, now in order to really check that this is continuous, you would need to do the same thing for these other flavors of basis open sets. And then you would also have to check this reverse direction as well. Maybe I'll leave that as an exercise though. And now we'll move on. Okay, so it turns out that if we've got a surjective map, then we can kind of build a topology out of that. We'll know that as the quotient topology. So here's how it goes. Let's say that X is a topological space, Y is just any set, and then P is a surjection from X to Y. Then here's how we'll define that quotient topology. V, which is a subset of Y, is open in the quotient topology, induced by P, so that's the word here, it's induced by our map P, if and only if the pre-image of V under P is open in X. So again, that's how we build a topology just out of a surjective map. Okay, so now let's look at an example of that happening. Let's say P goes from R to A. A is this set with 5 elements, and we'll just call them A, B, C, D, E. And P of X is going to be equal to A if X is less than 0. It's equal to b if x is 0, c if x is between 0 and 1, d if x is equal to 1, and e if x is bigger than 1. So I guess we could make a picture of what's going on here, and that wouldn't be too bad. So let's say this right here is the point 0. Let's say this right here is the point 1. Then observe that the point 0 is going to get mapped to B. The point 1 is going to get mapped to D. And then everything over here is going to get mapped to A. Everything between 0 and 1 is going to get mapped to C. And then everything over here is going to get mapped to E. And now we can build the quotient topology using this rule over here. So let's just start looking at pre-images of subsets of A. So let's observe that the pre-image of the singleton A is going to be the interval from minus infinity to 0, which is open, but that tells us that this singleton containing A is open in the quotient topology. Notice also that the pre-image of the singleton containing C, which is from 0 to 1, is also open, but that tells us that the singleton containing C is also open. And then finally, or maybe not finally, but with singletons being open, the singleton containing E, if we take its pre-image, we get the interval from 1 to infinity, which is open, which tells us that the singleton containing E is an open set in this quotient topology. Now let's compare that to, and I'll just say this in words, the pre-image of the singleton containing B is this, well, this set, which is just the singleton 0. But we know that singletons are not open in the Euclidean topology on A. And I guess I should have said we're taking the standard or Euclidean topology on A. So that means that the singleton containing B and the singleton containing D are not open. So we could collect that here. So the singleton containing B, the singleton containing D, these are not open. Great. And then actually, I think that these 1, 2, 3 singletons can really serve as a basis for the quotient topology. Now you would have to check this, but I don't think it's too hard to check, which would tell us that all open sets can be built out of, well, those 3. So let's see, we would have the empty set, and then after that we would have everything, and then we would have the singleton containing A, the singleton containing C, the singleton containing E. We would have the doubleton AC, the doubleton AE, and so on and so forth. Oh, but now that I look at this, we're missing some open sets when we do this. Notice that if we, for instance, take the pre-image of the set containing A, B, C, so let's look at A, B, C, observe that that's going to give us the interval from minus infinity to 1, which is an open set. And so I guess that we need sets like that as well. That like patches this hole that would occur where B gets sent. So here we could put like the set containing A, B, C here as well. And then I guess a companion to that would be the set containing what? Maybe C, and then D, and then E. And now I think we're kind of close-ish to a complete set here. We need some more doubletons. Notice that there are going to be there are going to be 3 of these. So I guess we could, insert this here, CE. Great. And then, well, is that all of the open sets? Well, I'll let you check and decide if we've got all open sets right there. I think we're close though, and at least we have a path for gathering all of the open sets in this quotient topology. Okay, so let's see where we can go from here. Okay, so here's another method of getting at the same thing as this kind of idea over here, and that is via the notion of equivalence relation and equivalence classes. So let's say we've got tilde, which is an equivalence relation on X. Now, if you need to review the notion of equivalence relations and equivalence classes, I urge you to check out the course that I have on Introduction to Proofwriting. There's a whole section on equivalence relations. Okay, so we've got an equivalence relation on X. Then we can build these so-called equivalence classes. We'll use this notation here, which is bracket X. So that's going to be all Y in X, where X tilde Y. So X is equivalent to Y. And then we can make the set of all equivalence classes. We might call that X mod tilde or X star. So again, that's just the set of all equivalence classes. Now let's define a a function P, which goes from X to X star, and it just takes an element of X and sends it to its equivalence class. So let's observe over here, that's clearly a surjection. In fact, it's kind of a natural surjection from a set to maybe the quotient space, if you will, the quotient set under the equivalence relation. Okay, and then observe that in the quotient topology as defined over here, we have a set V of X star is open if and only if its pre-image is open in the original space. But notice that the pre-image of V is simply going to be the union over all equivalence classes in V and of those equivalence classes. Now observe that V is in X star. X star is the set of equivalence classes. That means V is made up of equivalence classes. That's why we can say this thing right here. Now let's look at an example. This might look the same as one of the examples we saw before, but it's a little bit different. Let's say that X is again the unit square. And then let's say that 0y and 1y are going to be equivalent under our equivalence relation. So that's like gluing as we saw before. This notion of gluing is the same thing as being equivalent. Maybe the equivalence relation is the careful way of doing the gluing. And then let's say that x1 is equivalent, or sorry, x11 and x21 are going to be equivalent regardless of the x1 and the x2 that you have. Okay, so let's say that's our square. Let's say that this is 0, 0. Let's say that this is 1, 0. This is the point 1, 1. And over here is the point 0, 1. So let's see. We need to identify all 0y with all 1y. So that's like identifying this edge right here with this edge right here, keeping the same orientation. So that would start by gluing it together into a cylinder. Okay, and then, well, let's maybe put a dot over here because this is the part that's giving this yellow identification. Okay, and then, well, let's put a dot over here and observe that's saying that everything on this top edge is shrunk to a point. Everything on that top edge is the same in light of the equivalence relation, if you will. Okay, so let's see what this gives us. So the first step is to make it into a cylinder, and then we're going to shrink one side of the cylinder to a point. Observe that that's going to give us a cone. So let's see if we can get a nice picture of a cone like that. I think that's probably good enough. And then here we've got this thing right here, which is the tip of the cone. That's from this top edge. And then perhaps we could just put a line down here showing the seam. And now, well, we could play the same game that we did before about finding open sets, but let's say we went over here and we put a little top to this cone and we looked at the pre-image of that bit right there. And let's just say that it does not include the boundary at the bottom. Well, look, if we take the pre-image, that's pretty clearly going to give us this strip right here. Now again, we're not including the boundary on either of them. So this is open in the subspace topology. And then this one is open in, well, kind of subspace topology, looking at it in R3. But we're not really thinking about this in R3. We're thinking about this picture as occurring in this weird quotient space, which is the set of equivalence classes. But needless to say, since this pre-image is open, that means our original set is open, keeping in mind our rule right here. And then I guess we could do another one if we wanted to. We could take like a little bubble here around the seam, and that's going to give us something like that. Again, we're not including the boundary. The pre-image of that bubble is an open set over here in the subspace topology. That means that the bubble over there is an open set in the quotient topology. Okay, so now let's carefully write down this notion of a saturated set, which we talked about before. So a subset C of X is called saturated if whenever C intersects with the pre-image of a singleton, the pre-image of that singleton is completely contained in C. And so let's observe that the purple set over here is a saturated set. And that's because we built it out of a pre-image. But now let's look at instead this blue set right here. And the image of the blue set is the same thing as the image of the magenta set, but this blue set would not be saturated. And that's because if you took a point over here in the magenta set and you took its pre-image, notice it's going to have a pre-image over here and it's going to have a pre-image over here. So that means the blue set didn't contain all points from the pre-image. Okay, so anyway, the important thing here is that if P is a quotient map, then it may not be an open map as we saw, but it does map saturated open sets to open sets. And so it's open in a sense if you look at the correct type of open sets, those being saturated open sets. Okay, so now we're going to look at a pretty important a classic result. So now for our big result of the day, which can kind of be thought of as like the first isomorphism theorem in topology, if you will. It's not an exact comparison, but you might recall the first isomorphism theorem from, let's see, a group theory class, or it exists in rings as well, even in vector spaces. So in fact, it exists categorically, and this would be the version of it in the category of topological spaces, if you're into that kind of thing. Okay, so let's start with F, which is a surjective continuous map. So again, let's recall that in the case of groups, we may not have a surjection, but the first isomorphism theorem just talks about what's happening to the image, so we might as well have a surjection. And within groups, we have a group homomorphism. And here we've got a continuous map. And that's because the role of a group homomorphism when you're talking about groups is played by continuous maps when you're talking about topological spaces. So that's the parallel that's going on here. Then after that, we want to define an equivalence relation on X, where x1 is equivalent to x2 if and only if f of x1 is equal to f of x2. So this is like taking the kernel, if you will, in group theory. We don't really have the notion of a kernel, but this is kind of the idea behind this. Now we have x star in this equivalence relation is just the pre-image of all singletons in Y. That's pretty easy to show. And now next up, what we want to do is give x star the quotient topology, and we'll prove two things. The first is that F induces a continuous bijection, which we'll call F bar, and that goes from x star to Y. And then F bar is a homeomorphism if and only if F is a quotient map. And so notice that homeomorphism is like the idea of an isomorphism in a topological space. Again, we've got this kind of commutative diagram, which is pretty similar to the commutative diagram that you would have in group theory. Then we're going to have one other result too, but let's prove this one first. Okay, so the first thing to prove is that F bar is a bijection, but notice that it's kind of clearly onto, and it's clearly onto because F itself is onto. So now let's prove that F bar is injective. And so it's got to be onto and it's got to be one-to-one in order to be bijective. So let's suppose that F bar applied to x1 is equal to F bar applied to x2. And I should say the equivalence class of x1 and the equivalence class of x2. But then that is going to give us f of x1 is equal to f of x2. And I guess I should say here, because the induction of f to f bar means that what f bar does is it sends an equivalence class to where the original function mapped the element. Okay, good. But okay, we've got f of x1 equals f of x2, but then that's equivalent to saying that x1 is equivalent to x2 by our rule here. but then that's equivalent to saying that the two equivalence classes are the same. But that's what we needed for this thing to be an injective map. Okay, so now we need to show that it's continuous. So let's say that V inside of Y is open, and we want to look at the pre-image of V. Okay, but notice that we know immediately that the pre-image of V under F is open because F is a continuous map. But then let's note the following, and that is the pre-image of V under F bar, or sorry, the pre-image of V under F can be decomposed as the pre-image under P, the projection map, applied to the pre-image under F bar. But we know that P inverse is a quotient map inducing the quotient topology. So the fact that this is open, well, implies that the pre-image under F bar is open, just by definition of the quotient topology. And so that means that we've got this first bit right here, a continuous bijection. Okay, so now we'll show that F bar is a homeomorphism if and only if F is a quotient map. So notice that F being a quotient map, all we'll need to show is, let's see, this direction right here, because the continuity of F, which we're assuming, gives us this direction right here. So let's start with this forward direction. So F bar is a homeomorphism. And then let's suppose that the pre-image of V inside of X is open. But now what we want to do is show that V is open. But note that we can write V in the following kind of tricky way. And that is V is going to be equal to F bar applied to P applied to the pre-image of V. But now, again, that's open because F bar is a homeomorphism. Okay, so now what about the reverse direction? Well, I'll maybe leave the reverse direction as a little bit of a homework exercise. It's not actually that bad. And now let's look at the next result that we can add to this theorem. Okay, so to finish this thing off, we'll show that if Y is Hausdorff, then X star is also Hausdorff. Okay, so let's take, let's see, the equivalence class built from X1, which is not equal to the equivalence class built from X2 inside of X star. And what we want to do is find two open sets, one that contains this element or equivalence class, one that contains this, and they do not overlap. But how can we do that? Well, since these are not equal, that tells us that if we apply F bar to them, we'll get something that's not equal. And that's because F bar is a bijection. Well, we proved that here, it's a continuous bijection. But that tells us that F applied to X1 is not equal to F applied to X2. I think we could have gotten right there from the beginning, but that's okay. And this is occurring in Y. So this not equality is occurring in Y. But then we can find open sets V1 and V2 inside of Y with f of x1 contains V1, and then f of x2 is contained inside of V2 with the intersection being empty. That's using the Hausdorff condition on Y. Okay, but now let's note the following, which is going to pretty much finish this thing off. And that is that the singleton, or just like singleton inside of X star of X1 is contained in the F bar pre-image of V1. And then the equivalence class for X2 is contained in the F bar pre-image of V2. And then also, these things are both open in the quotient topology by how we define the quotient topology. And then, okay, so that's the first thing that we'll note, is that we've got open sets containing the right elements. And now let's show that these open sets do not overlap. So we can do that by supposing that they do overlap. So let's say we've got a equivalence class X that's inside of F bar pre-image of V1 intersected with F bar pre-image of V2. But then I think we can smash these together to give that F bar pre-image of V1 intersected with V2, by just how functions on sets work with intersection. But now we can apply F bar to this, but applying F bar to this is the same thing as applying F to the element. And we see that this element is inside of V1 intersect V2, which is the empty set. So that means that, well, if this is the empty set, then this object right here is also the empty set, which is what we need for X star to be Hausdorff. Okay, so now I'm going to leave you with some exercises. Okay, so here's some exercises for you. The first is to show that if you compose quotient maps, you get another quotient map. The next one defines this notion of a retraction. So let's say we've got a subset A of X, and we've got a map from X to A. And that map is continuous, and it satisfies this condition that if you restrict R to A, you get the identity on A. So what that means is that R of A equals A for all A in A. So this map goes from X to A, but it fixes all of the elements of A. Now, what you want to do is show that R is a quotient map. Okay, so next up, let's define an equivalence relation on R2 by the following. So x1, y1 is equivalent to x2, y2, if and only if x1 squared plus y1 squared is x2 squared plus y2 squared. And then what you want to do here, this is kind of a soft question. So what does X star, which is the quotient space, R2 mod tilde, what does that look like? And then, well, what do some open sets look like in X star? And that's a good place to stop.